In this video we're going to be talking about magnetism. And magnetism has been known of for thousands of years. There are naturally occurring magnetic rocks in the Earth's crust, and when you stumble across one of these rocks, it's fairly obvious that it's attracted to other magnetic rocks or other metallic rocks. It took a long time, but people eventually found use for these magnets and created something called a compass. And a compass is really just a magnet that is free to rotate. So it gets aligned with the Earth's magnetic field, so that one end always points towards the north end of the Earth and the other end always points towards the south. Here we're talking about geographic north and geographic south. So because this end seemed to point towards the north of the Earth, we called it the North Pole. Or we simplify that sometimes with just labeling it as the N pole. And then the other side obviously is the South Pole. And we simplify that with just an S for South Pole. So we can use a compass to map out a magnetic field. So if we had a bar magnet like this one, we can put our compass at various positions and we can see that the magnetic field at this point is in this direction. Over here it's in this direction, over here it's in this direction, and we can keep drawing the lines of the magnetic field around this magnet. And after experimenting, we discovered that opposites attract, just like in electricity. So because this is the north pole of our compass, because it's attracted to this end of the bar magnet, we now know this end of the bar magnet must be a south pole. And this part of the magnet, which is the south pole of the compass, must be attracted to the north pole of the magnet. So we're now able to use our compass to determine the polarity, or which pole we are looking at on a magnet. And we can use the compass to trace out the lines of the magnetic field. So what we see is that on a north pole, the magnetic field always points away, and at a south pole, it always points towards the magnet. Now, this has some implications for the Earth's magnetic field. Obviously, if the north pole of our compass is being attracted towards a south pole, the geographic north of the Earth is actually a south pole magnetically. And the geographic south of the Earth is actually a magnetic north. Now again, this is just a consequence of us labeling our compass as one end being the North Pole and the other end being the South Pole. So what you can see is the magnetic field here around a typical bar magnet, pointing away from the north and into the south. So around the year 1820, a Dutch physicist by the name of Oersted was looking at doing experiments in electricity, and he noticed that whenever he had an electric current in a wire, that this electric current flowing in this direction caused his compass needle to move. So what Oersted in effect discovered is that moving electric charges create magnetic fields. Okay. And that's what actually is creating the magnetic field of the Earth. The center of the Earth is a molten liquid, lava almost, and the rotation of the Earth causes that lava to rotate, and those moving electric charges create the magnetic field of the Earth. Same thing here. We have a current moving in this direction, and it affects the compass. The magnetic field created by this wire affects the compass. The symbol for magnetic field is a B. It's a vector quantity. And the units that we measure magnetic field in are Teslas, which is an uppercase T, which is unfortunate because we also use T for a number of things: period, time, temperature. It's also now the unit for magnetic field strength, which is Tesla. So Ørsted discovered that moving magnetic charges create magnetic fields. And he also created what we call the right-hand rule, because you basically use your right hand to determine the direction of the magnetic field. And we're going to have two different right-hand rules, so I'm going to label this right-hand rule number 1. And to simplify it so I don't have to write out right-hand rule all the time, I'm just going to call it RHR number 1. Right-hand rule number 1. So in right-hand rule number 1, you take your right hand and you grab the wire and you point your thumb in the direction of the electric current. So obviously we couldn't grab the wire in any other direction other than this direction, because my thumb has to be pointing in the direction of the current. And what happens is my fingers going around the wire trace out the direction of the magnetic field, B. So you can see here in these diagrams the direction of the magnetic field around this current. So the magnetic field around a wire is circular. It goes all the way around, following the path of my fingers as I grab the wire. And we call that our right-hand rule. So we can now determine the magnetic field around a wire. Now obviously we can't draw these very fancy diagrams, so we're just going to go over a couple of things about notation. If I have an electric current going in this direction and I want to figure out the magnetic field around it, I would obviously use my right hand pointing my thumb in the direction of the current, and what I would find is that the magnetic field kind of goes around like this. Even these diagrams, it's a little bit confusing. So what we know is that in this region above the wire, the magnetic field is coming out of the page, and in this region below the wire, it's going into the page. So what we really need is some symbol to represent those two directions: into the page and out of the page. So into the page, what we're really looking at is the vector. The vector of the magnetic field is coming out of the page. So if you think of a vector, the point that's coming out of the page would be the very tip of the arrow. So it would look like the tip of the arrow, so that point coming out of the page. So to represent out of the page, we basically just draw dots. So out of the page is a dot. Into the page would be the other end of the arrow, and if this was like a bow and arrow that you've actually fired, what you would have at one end would be the feathers of the arrow. So that would look like the feathers going into the page would look like, an X. So we have circles to represent out of the page and X's to represent into the page. And that prevents, we don't have to draw these weird kind of arrows. So we know that above this wire, the magnetic field is coming out of the page. Below this wire, it's going into the page. Some textbooks, you'll see these drawn in a circle. My notation, I just use the dot and the X. So that means we can draw a region of magnetic field going into the page as just in this region here, this is the magnetic field going into the page. Okay, so in the next video, we'll actually talk about how magnetic fields get created.